Hello, this is a lecture for section 1.1, Functions and Function Notation. We should start at the beginning. What is a function? Well, very simply put, a function is a rule that describes a relationship between inputs and outputs. The inputs are referred to as the independent quantity or variable, and the outputs are referred to as the dependent quantity or variable. And the key thing here is that each input value uniquely determines only one output value. We would say that the output is a function of the input. So the key point here again is that each input results in one and only one output. All right, let's look at some examples of functions, or some examples that might be functions. At a vending machine, is the item code a function of the price, or would the price be a function of the item code? You have to ask yourself which thing uniquely determines the other, right? Or if we input an item code, will there be only one price? Yeah, each item can only have one price. If we input a price, would there be only one item code that was that price? Probably not, right? Most vending machines, if it's beverages, they have several different types of beverages, and many times they all cost the same thing. If it's snacks, you may have several categories or several different prices, but there's usually multiple snacks that are that same price. All right, another example here, would we say, is temperature in degrees Celsius a function of the equivalent temperature in degrees Fahrenheit? Right, we all know we can convert Celsius to Fahrenheit. If we have one temperature in Celsius, is there only going to be one temperature in Fahrenheit? Yes, there is. So I could say that temperature in degrees Celsius is a function of the equivalent temperature in Fahrenheit. How about the other way around? Is temperature in degrees Fahrenheit a function of the equivalent temperature in degrees Celsius? Yeah, I say it is. We can convert one way to the other, but if it's, if it's 10 degrees Celsius, it's not going to be 2 different degrees Fahrenheit. It'll be some specific degree Fahrenheit. If it's 70 degrees Fahrenheit, it's going to be some specific temperature in Celsius. Okay. So this would be, we could say that degrees Celsius is a function of degrees Fahrenheit. We could also say that degrees Fahrenheit is a function of degrees Celsius. Lastly here, is your letter grade in class a function of the percentage grade you have? Or is the percentage grade you have a function of the letter grade you have? We have to ask again, given a percentage grade, is there only one letter grade you would get? Yes, if you have an 82%, you're going to get a B. If you have a 96%, you're going to get an A. There's only one letter that gets associated with each percentage grade. Does it work the other way around, though? Given a grade, can you determine what your percentage was? No, I don't think so. If you have an A in the class, if your class grades on a standard 10-point scale, if you have an A in the class, you may have had a 91%, you may have had a 97%. Anything in between 90 and 100, in fact, as a percentage would give you a grade of A. So we would say that your letter grade is a function of the percentage, but we could not say that your percentage grade is a function of the letter. All right. There's a specific type of function called a one-to-one function. This is a relationship in which each input corresponds to exactly one output, and each output corresponds to exactly one input. Thus, we call it a one-to-one function. In the examples that we just looked at, the Celsius to Fahrenheit and Fahrenheit to Celsius functions are one-to-one, right? For each degree Celsius, there's only one temperature in Fahrenheit. For each temperature in Fahrenheit, there's only one temperature in Celsius. All right, when we talk about functions in algebra and mathematics classes, we use function notation. All right, with function notation, we name the function. We usually use a letter like F or G or H, something like that. And then in parentheses, we put what that function is expecting to receive as its input, right? And then what that function equals is going to be the function output. All right, so this notation would read F of input equals output in the most generic sense. In a more specific sense, we might see something like this. We tend to use the input variables as x's and the outputs as y's. So we might read this f of x. We might read this function description here as f of x equals y. Okay. Another example might be something like this. F of x equals 2x, where the function is defined by 2x. It says the rule for the function that relates inputs to outputs. The rule for the function is you take the input x, whatever that value is, you multiply it by 2, and then you will get your output. That's going to be the value of y. All right. So, for example, here if we define a function called d to be the number of days in a given month, and we'll forget about leap year here, then we could say that d of June equals 30, right? The rule here is how many days are in the month. The input is the month. The output, the result, is how many days that month actually has. Okay, we can also look at functions as tables of values, right? And we're not going to, we've got some examples here that we don't know what the rule is. We might guess at it, but we don't know what the rule is. And with these functions, all we know is the inputs and the outputs. But could we determine with these tables, all we know is the inputs and the outputs. Can we determine if these tables actually represent functions? Well, the key thing that we want to look at here is, does each input uniquely correspond to one output? Or is there only one output that results from each input? So if we look at table A here, we can see an input of 3 results in an output of 8. -1 gives 6, 9, 2, 8, 6, 0, 0. So is there any input that gives us 2 different outputs? No, not at all. So I would say that yes, this is a function. Is this a one-to-one function? In other words, does each input correspond with only one output, and does each output come from only one input? Is there a one-to-one relationship? Well, 3 goes with 8, -1 with 6, 9, 2, 8, 6. Uh-oh, there's a little bit of a problem here. Look, when I input -1 into the function, I get 6 out. When I input -8 into the function, I also get 6 out. So even though it absolutely is a function, it is not one-to-one. Okay? So I might say function, but not one-to-one. All right, look at the table B here. Here when I have an input of 1, the output is 7. 9 produces 2. 6 corresponds to -5. 4 to 0. Look at this 1. When I put input 1 in this last row in the table, my output is 5. That's a problem here because when I input 1 in the first row, the output is 7. When I input 1 last row, the output is 5. Well, because that same input resulted in 2 different outputs, I have to say that this is not a function. We might call that a relation between inputs and outputs, but it's not a function because it's not unique. Each input does not uniquely result in one output. Look at table C here. Here our inputs are 1, 2, 3, 4, and 5. The outputs 2, 3, 4, 5, and 6, respectively. One results in 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6. Is it a function? Yes, I would say that is. There's no evidence that the same input results in 2 different outputs. So I would say function. It is a function. Is it one-to-one? Let's see. Is there any situation where 2 different inputs resulted in the same output? No, there isn't. So this is a function, and this function is one-to-one. Okay, look at this last option here, this last table. 7 results in 2, 1, input of 1 gives us output of 7, negative 9 to 4, 0 to 7, 6 to 1. Well, let's see. There's no repeats here on the input, so there's no possibility from the evidence given that this is not a function, so I would say, yeah, it is a function. Is it one-to-one? Well, when I look over here at these outputs, I don't see any repeats. 7 goes to 2, 2 comes from 7. 1 results in 6, 6 results from 1. Negative 9 corresponds to 4, 4 corresponds to negative 9. I don't see any repeats anywhere here, so I would say this is a function, and it is one-to-one. All right. Okay, so the definition of a function is that each input can result in only one output. And the definition of a one-to-one function is that each output must come from only one input. All right. Evaluating functions simply means finding the output of the function given the input. Right? So here we have a table. We have some R values in the first row of the table and P of R in the second row of the table. So this is the function here is P. It's expecting R as its input. So the first row in that table is inputs. The second row in that table is outputs. All right? If we were to evaluate P of 3, this is saying that the function called P is expecting 3 as its input. All right? So or 3 is the value of R. Right? So we go up here and we find where R is 3. There it is right there. When R is 3, the corresponding output is 7. So I would say that P of 3 equals 7. Okay, and again, that first row is our inputs. That second row there is our outputs. Okay. The second part of this example says solve P of R equals 2. All right, so what's it telling me there? It's saying me that the value that P of R is 2. So what I'm wanting to do here is I'm wanting to find which R results in 2, right? I want to find the input when P of R equals 2. So let's look at the output, or the P of R row, and let's see if we can find 2. There it is right there. So a result of 2, or an output of 2, comes from, or results from, an input of 0, right? So if P of R equals 2, I would have to say that R equals 0. All right? So when we evaluate a function, we're looking for the output of the function. If we're solving a function, we're looking for the input that gives us a specific output. All right, graphs of functions are interesting. Here we have 3 examples of graphs. They may or may not actually be a function, though. Okay, how would I determine if a graph was in fact a function? Well, again, the definition of a function says that each input will produce or result in only one output. So when we're looking at a graph, that means each x coordinate, each value for x can only have one y coordinate, right? So if I look at this first example here, this looks like a polynomial of degree 3, this graph. Could I say that that's a function? Does each, if I think about every single point on this graph, like here's a point right here where the x coordinate is -2, the y coordinate is 0. Look, it goes through the origin where both the x and the y coordinates are 0. Here's another point over here where the x coordinate is +2, y coordinate is 0, several other points on there. But is there any x coordinate, any value of x that can have 2 values of y? The answer to that is no. So I would have to say that this is a function. And some of you may have heard of the vertical line test. The vertical line test is an easy way to determine if a graph is in fact a graph of a function. All right, the vertical line test says, there it is, if no vertical line would cross the graph in more than one place, then that graph is a function. All right, so let's see. I don't know if I can get them both to show. Maybe I'll fold my page here. It's kind of old school. We can do things like this, right? Fold the page. There we go. They're both showing. Does this first function pass the vertical line test? Well, let's see. What would some vertical lines be? If I drew one here, well, it only interacts with that graph once. I could draw another one here, here. Any vertical line that I can imagine drawing on there is only going to intersect that graph in one place. So this does pass the vertical line test. Tells us that it's a function. How do I determine if this function is one-to-one? Well, the definition of a one-to-one function says that each x produces one y, or each input produces one output. And we do usually refer to x's as inputs and y's as outputs, right? X tends to be is usually the independent variable, and y is usually the dependent variable, or the output variable. Y usually depends on the variable of x. All right, so looking at this, well, when x, let's see, if we want to know if it's one-to-one, we have to look at the y's, right? When y is 0, look, x can be either -2, 0, or +2. So that means this is not one-to-one. So it's a function, but I have to say not one-to-one. There's an easy way. You may have heard of the horizontal line test. The horizontal line test is an easy way to determine if a graph is a one-to-one function. The horizontal line test says that if you can draw a horizontal line, if you can imagine any horizontal line that does not intersect the graph in more than one place, it's a one-to-one function. This example here, though, however, look at this. We already talked about it, but the horizontal axis here, right, or a horizontal line, right, at y = 0, that horizontal line, that interacts or intersects that graph in 3 places. The line y = 0, 3 places. That's why that is not a one-to-one function. It fails the horizontal line test. And there are several other that I can imagine drawing there as well, but it will fail. Okay, if we look at the second graph here, that's a linear function. Is that one one-to-one? Well, first of all, is it a function? Oh yeah, that one very quickly does pass the vertical line test, right? Let's move this up again. It does pass the vertical line test. There's no vertical line that I can imagine that would intersect with that graph more than one time. Also, there's no horizontal line that I can imagine that would intersect that graph in more than one place. So this passes both the horizontal and the vertical line test. So I would say, yes, it is a function, and it is one-to-one, right? And one-to-one. It passes both the horizontal and vertical line tests. Look at the last graph here, the circle. Well, the circle is not a function, is it? Look, it does not pass the vertical line test. It intersects the graph 2 places there. It also does not pass the horizontal line test. It intersects the graph in 2 places there. So I have to say that this last graph here is not a function. Doesn't even really matter if it's not one-to-one or not, since it's not a function. But I might also say it's not a function and not one-to-one. Okay, circles are not functions. All right. Okay, we can solve or evaluate functions based on the graph as well. Graphs are really powerful. Given any input or any x value, we can determine the y value that x corresponds to, right? By simply identifying the coordinates of any point on the graph, right? Or at least the part that's documented for us. Here we have a graph. This is again, this looks like a cubic polynomial. We have this graph, and we know that it's a function. We've already decided that it's not one-to-one, but we can evaluate this function, right? If we want to evaluate f of -1, right? The key here is I don't know the formula or the algebraic representation of this function. I don't know that formula. I just know the graph of it. But I can find the output that results from an input of -1, because on a graph, almost always the x's are the inputs or the independent variable, and almost always y, this is y up here, is the output or the dependent variable, because the value dependent, the value of y depends on what the value of x is. So given that if we want to evaluate f of -1, this is saying that x is -1. So we find where x is -1 on the graph, right? Or we find the point on the graph that has a coordinate of -1. And it looks like it's right there. And in fact, we're going to just sort of assume that it's a whole number there. And then the coordinates of that point would be x equals -1, y equals 3. Okay? So, because those are our x, y coordinates on the graph. So when x is -1, y is 3. So I know that f of -1 equals 3, because when x is -1, y is 3. Okay? Now part B here says solve f of x equals 0. This is saying find the x, or find the input that gives us an output of 0, right? So what I want to do, and remember f of x function notation for this function, f of x equals y. It's really just function notation for the y, or the output. So I want to find where y equals 0. Where y equals 0. Let's see, where is y equal to 0? Well, the point on the graph that has a y coordinate of 0 is right here at the origin. The x coordinate also happens to be 0. Okay, so I would say that x equals 0 when f of x equals 0. Or that an input of 0 gives us an output of 0. Right, so we can evaluate functions from the graph itself. And we can also evaluate, solve, analyze functions when they're represented algebraically, or when we have the actual formula, or the actual, the actual rule for the function. All right, so here we have this function called t. It expects as its input m. Okay, so this function is defined, t of m is equal to m squared plus 3m. The rule for this function says take some input, some value for m, square it, okay? Then add to that value 3 times the input, right? So if I want to evaluate t of 4, what I'm saying here is that m equals 4. So t of 4, I want to substitute 4 in for m. T of 4 is going to be 4 squared plus 3 times 4, right? 4 squared is 16, and 3 times 4 is 12, so 16 plus 12 is 28. So I would say t of 4 equals 28. Okay? Part B says solve t of m equals -2. Okay, this is now telling me that the output, or t of m, equals -2. It's kind of like the y if it was on a graph, right? So what do I want to do here? If I'm solving, I'm looking for the input that's going to give me the output of -2. So I just want to substitute -2 in for the t of m and solve. I want to say -2 equals m squared plus 3m, and I want to solve for m. Okay, well, that's a quadratic equation. So to solve for m, I have to set it equal to 0. So I'll add 2 to both sides, and I'll have 0 equals m squared plus 3m plus 2, and I'll solve. Let's see, I think that factors, so I can solve that quadratic equation by factoring. We'll move up here to do it. So 0 will equal, what are my factors here? Let's see. I think m plus 1 times m plus 2 equals m squared plus 3m plus 2. So either 0 equals m plus 1 or 0 equals m plus 2. So I have two solutions here, right? Solving this first equation for m means I have to subtract 1 from both sides. So m equals -1. The second equation involves solving the second equation involves subtracting 2 from both sides, so m equals -2. So I have two solutions here. I have two inputs that will result in -2 as an output, right? I could check those answers. I could check those answers by evaluating t of -1 and t of -2. Here, let's do it. Let's check it up here. T of -1, that's going to be equal to -1 squared plus 3 times -1. Well, that's +1 minus 3, or -2. Yep, that's what we wanted it to be, so that's true. Now let's check the other one, t of -2. T of -2, well, that's going to be -2 squared plus 3 times -2. Well, is that +4 minus 6? That's -2 again. So yeah, that does check. Those solutions are correct. Right. Now part C of this example is interesting. It says evaluate t of 3 minus t of -3. So what's this saying? It's saying, well, I need to find the value of t of 3, whatever that is. I need to subtract from it the value of t of -3. Right? Well, I can do that all at once, right? T of 3 means I just want to substitute 3 in for m. So that's going to be m squared plus, oh, I'm sorry, that's going to be 3. I'm substituting 3 in for m, so that's going to be 3 squared plus 3 times 3. Okay. Then I want to subtract from that t of -3. Well, I want to subtract the whole thing, so let me put a bracket in there. T of -3 is going to be -3 squared. Make sure I use parentheses around that negative. And then plus 3 times -3. Right? So what is that? Let's see, 9 plus 9 minus, what does this end up being? This ends up being 9 minus 9. So we're just subtracting out 0. It's just 9 plus 9, or 18. All right? So t of 3 minus t of -3 is 18. Now the last topic that we have in this section 1.1, the first section of chapter 1, is the basic toolkit functions. This is very important that you're very familiar with these functions. I don't like to say memorized, because memorizing is kind of silly, but you do need to make sure that you know that if you see f of x equal 2, that you know that that's the constant function, and that it's going to be a horizontal line right at y equals 2. Okay, if you, the identity function, f of x equals x, you need to know that the graph of that is going to be this vertical, or I'm sorry, this linear function where all the x and y coordinates are the same, the identity function. Right? The absolute value function looks like this, f of x equals the absolute value of x. We have the quadratic function, f of x equals x squared. It's a parabola sitting right on the origin. We have the cubic function, f of x equals x cubed. Okay, looks like this guy. All right, and then a few more. We've got the square root function. Looks like this, f of x equals the square root of x. We have the cube root function, f of x equals the cubed root of x. Looks like that. The reciprocal function, f equals 1 over x. It's this guy. And then lastly, the reciprocal squared function, f of x equals 1 over x squared. All right. It's very important that you know these toolkit functions, that you know what they're called, what they look like, and what the formula for them is, because we will be using these extensively throughout the course. And I think the next area that this is most important is when we go over transformations, which is in a few lessons. All right. So that ends the lecture for section 1.1. If you have questions about anything here, please do not hesitate to send those questions to your instructor.